All right. So I've got a recording here for you, this video, and um what I want to do here is I want to cover um like some holes, some things that we missed in our lecture just because we ran out of time. All right, and you're going to need this information. I've tried to make it really directly relevant to your homework assignment. Okay, so it's going to be a little bit longer video. All right, but stick with it. It's pretty important, and it's going to help you with your homework assignment. Okay, do it in little chunks if you want to. That's fine. Um, so here's the situation. Let's suppose we've got um, a metal bar there and a metal sphere. And the sphere is kept somehow at a voltage of -5. So maybe we put a bunch of extra electrons on there, for example. And then the bar is kept at +10. So we subtracted off some electrons to leave it with a positive charge there. Okay, now then let's suppose that we had some kind of special probe and we're trying to measure the voltage, all right? The voltage in all these different places all around, okay? So we might take our voltage probe and start with it right here. And we're going to go, oh, that's 10 volts. Okay, cool. And then maybe we move away and we get over here, all right, and we find that that's 8 volts. And we're like, oh, cool. And then we move out a little bit further, and then it's gone down to 6, and then to 4, 2, 0, -2. And of course, on the sphere over here, it's -5. Okay, just like that. And then let's say that what we want to do is let's find all of the places where the voltage is 8. Okay, 8 volts. And so we take our little probe and we move it all around looking for all where the 8s are. And we find it like over here and over here and over here and up here and up here and up here. And we want to find all these places. And okay, and we actually go all the way around it. Okay, and we're going to find something like this. On that particular curve, every place is 8 volts. Okay, so that voltage is a potential. So that is an equipotential curve. Okay, in case you aren't sure what I'm saying there. All right, equal potential, equal voltage all the way around on that thing there. Okay. Okay, now we've got all the places where it's 8. Now let's find all the places where it's 6. All right, so we probe around, we probe around, we probe around. We map all those different places and we might find something like this. And then we do the 4. Then we do the 2. And the 0. And the 0 might do something weird on us. Just like go out like, oops. It's not going to go like that. I mean, it's going to curve around here like this. Then do the -2. Okay. It's going to go something like this. And then we should have a -4 on there too. Number of -4 is going to be super tight on there. Sort of like that. Okay. Now what we've drawn here is we've drawn all the equipotential surfaces at 2 volt intervals for this configuration. Okay. So that's what that is. Now that's not something you're going to have to do. All right. During non-COVID times, we would do that in a lab. Okay. And it's pretty interesting. But unfortunately, you know, we're stuck with computer stuff. Okay, so there's the voltages. Now, what we want to do is we want to figure out what would the electric field be like. Okay, so remember that the electric field is related to the voltage by the derivative. Okay, now that's magnitude. If we need direction, then we end up having to use a little different approach here like that. So that'll get a direction for us. Or if we're lucky, we can just slap an I or a J, something like that on there and it'll be fine. Okay. Okay, now, so draw some electric fields on here. Let's start here. Okay, now the electric field has to be at right angles to the voltage. Okay, it has to be at right angles to the voltage. And so that means it's going to come straight out like this. And it's going to right down the middle here, it's going to hit all these guys straight across. Boom, 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 boom. Okay, and it's going to start at the positive and end at the negative. Okay, now let's pick another one. All right, maybe over here. Okay, so I'm going to come out here. But now you see I'm going to have a little bit of a curve because I got to hit that next one also at 90 degrees. All right, something like this. Okay, and I'm going to have to start curving back in here. All right, now we're not really sure what's going on here, so we got to use our imagination a little bit. We're going to have to curve through space, but we got to hit this one at 90 degrees, hit the next one at 90 degrees, sort of like this, okay? And we can just sort of keep on doing that, sort of like this. Oops. Coming around here. And then on the other side, we're going to have something similar. Coming out. Back in. Okay. There'll be some field lines coming in this way. And some field lines coming out this way. Here. Here. Yeah, this is really boring to watch. And here. Okay, sort of like that. Okay. So now what I've got is I've got a nice little picture there of my equipotential surfaces and my field lines. Okay. So again, the ones with the arrows are the field lines and the others are the equipotential surfaces. That's their voltage. Okay. Just like that. All right. Now, let's suppose that we wanted to try and figure out the value of the electric field somewhere. Okay, so to illustrate first, let's pick some place easy. Okay, so maybe we say right here. All right, at that spot right there, I want to know what is the electric field. Okay, so let's say that's A. I want to know what is the electric field at A. Okay. Well, what we have to do is we're going to come back to our definition up here, all right, and realize that the electric field is the derivative there. So since it's a real world thing and not a mathematical thing, we can say that the electric field then is minus delta V over delta X, okay, just like this. And so then we come back to our location of interest and we're like, okay, I know it's 8 over here and I know it's 6 over here. Okay, so we could say here that we're going to have minus our delta V, okay, and we'll go left to right, or right minus left. Okay, so end point minus beginning, just like if you were integrating, we'll go that way. So that means is we're going to have 6 minus 8. Okay, and then we need a distance. All right, now on your homework it would tell you what the distance was. I'm just going to make one up here. All right, and so let's say that distance across there is 2 centimeters. So I got 0.02 meters is my distance from one side to the other. Okay, so we have to put that in up here. So 0.02, just like that. Okay, so now 6 minus 8 is -2, but I've got minus -2, which turns it back to a positive. So I got 2 divided by 0.02, and so that should be 100. Okay, that's 100. Okay, now if we pick out a different location, okay, so maybe way up here. Okay, let's say in the middle right here. Okay, let me call that B. So if we want EB, okay, so let me zoom in on that. All right, again, still we know that this inside one is 8 and the outside voltage is still 6. Okay, and so what's different in this case is the distance. across here. And so maybe this is 1 centimeter instead of 2. All right, so maybe it's half as much. Okay, and so what's going to happen then, okay, so this was EA. So EB, we're going to have the same thing, minus our delta V over delta X. Got the same thing on top, minus 6 minus 8. But in the bottom, we get the 0.01. Okay, and then that's going to give us 200. Okay, just like that. So our electric field will be 200. All right. Now, as we have talked about electric fields, okay, our units have been newtons per coulomb. Newtons per coulomb. Okay. The thing about electric field is there are 2 different sets of units. Okay. One is newtons per coulomb, which we've been using. And if you're dealing with a force, if I want to know, oh, what's the force? If I've got a 10 coulomb charge and I'm in a 200 Newton per coulomb field, look at that. See, our coulombs just cancel right out and we're going to get 2,000 newtons. Okay. That works out just fine. Okay. However, if we were interested in something else, like, let's come over here and say, what's the voltage difference between this place and this place? All right, so that's a difference of 0.01. Okay, so maybe I got 1 centimeter in there. What's that going to be? Well, if you look here, we can do some algebra and we can figure out then that our delta V, okay, is just going to be minus EB delta X, like that. Okay, and but if we put newtons per coulomb in there, watch what happens. This is a little crazy. Okay, then I'm going to have, let's say it's, it's only 100 there. So I got 100 newtons per coulomb. That's a parenthesis. Sorry, that's too sloppy. Unacceptable. Minus 100 newtons per coulomb. And I come in there and put 0.01 meters. You see, I got a mess. Then I got a mess. Okay. But we can use a different set of units because what is this? It's a delta V over delta X, which means we could call these things volts per meter as well. So our electric field could be newtons per coulomb or volts per meter. Either one is going to be fine. And in our situation down here, if we come back in here, let's get rid of that. That's not helpful. Okay, but if we use our volts per meter unit, now you can see right away I lose my meters. Okay, just like that. And we're going to find out that we've got a negative 1 volt potential difference. That's supposed to be a V between the two sides. Okay, those 2 points. So we've got options there, and which set of units we use depends on what our situation is. Okay, sort of like that. Okay. All right. So on your homework, you'll have some problems like that where you have to make some estimates given some information. Okay, and you're going to work it just like we did there. Okay, so now let's do this. Let's put an x-axis right down the middle here. Boom. So on an x-axis. And we're going to call 0 is going to be right here. Okay. Now I don't really care about the y-axis, but that's x equals 0 right there. So that's the beginning of my thing. And now I want to think about the voltage as a function of position. Okay, so here we go. Here's my axis. Here's my 0. Okay, and my little bar extends across this whole region here. And then my sphere is all across this whole region here, like this. Okay, so there's my bar. Here's my sphere, just like that. Okay, and what we're going to do is we're going to graph potential here as a function of position. Now, on my bar, I know that the potential is 10 volts. Okay, so that's my 10 volt level right there. But I know on my sphere, it's -5. So that's going to be down here like this. Okay, so my voltage has to get from 10 down to -5 over that space. Okay, over that space. And so in this case right here, right, shooting right down the middle like that, it's pretty much going to be a straight line. Okay, and then you know what we did, remember we marked it at 8 and 6, 4, 2, -2, -4. Okay, so this corresponds to, well, let me get a different location. This corresponds to this position. This corresponds to this position, etc. Like that, okay? So, like with our voltage, we're actually making a picture of the landscape in terms of how steep it is, rather than looking above it and looking down like a topographical map, okay? I don't need all those. That's going to make it messy. Okay, so we've got right that there. Now, what's going to happen on the other side of the sphere? Okay, well, we don't have data, and we would just, you know, so I'm going to speculate. Okay, and so what I'm going to do is, because it's 10 volts and -5 volts, if we're a long ways away from this thing, we can't see that it's a 10 and a -5. It's going to look like a +5. Okay, it's going to blur together. And so what I think is going to happen is this thing's probably going to come up, rise up just a little bit, and then tail off. Okay, now on the other side, it's just going to slowly kind of curve away like this. It won't be linear. Okay, we only expect it to be linear in that interior portion, just like that. Okay, so if we think about now finding the electric field, okay, so in this region here, all right, the electric field is minus dV dx. And you can see that that's constant in that particular region right there, okay? That's going to be a constant value. Now, even though the slope is negative, remember it's minus the slope, Okay, so if we were going to come in here and let's say, let me try to put another graph right here with it of the electric field, okay, then what we're going to have in this region, all right, from right outside my bar to right outside my sphere, I'm going to have some constant value right there. Okay, now I don't know what it is. I don't know why I drew bars like that, but some constant value just like that. Okay, now what about, okay, what about this area on the bar? Okay, that area on the bar, the voltage is all 10. Okay, so it's constant. So what's the slope there? It's 0. All right, so that means across my bar, it's actually 0 like this. Okay, there. Now, if we keep going to the left on the other side of the bar, then we don't actually have a function for this. Okay, so let me call it V. I'll call it V left. We don't have a function for that. But if we did have a function for that, then we could just take its derivative, okay? And you can see it's going to drop off, boom. And so probably then we're going to end up with something that looks like this. Okay, it's going to probably go something like that, okay? There, right, because it's going to point the other direction, so it's negative, okay? So I've actually got a positive slope this time on my voltage, but it's negative times the slope, so that makes it negative again, okay? All right, then on the right hand side, okay, again over here, we don't actually have a function for this. We don't know what that is, but but if we had it, we could take its derivative and then we're going to be good to go. Okay, so we've got a positive slope there, which makes it becomes negative. Somewhere in here, it goes back to being 0. Okay, and so, we might have something like, I don't know, I'm just going to make this up. Something like this. Okay. It's going to go back down. Okay. All right. Again, I'm speculating here because we don't have a function. On your homework, there's going to be some questions like this, where you're going to have the voltage, and it's going to ask you for the electric field. Okay. And so you're going to be looking at slopes and derivatives of functions and that sort of thing. Okay. So it's pretty straightforward, but now you know how those things are related together there. All right. So one more thing I want to talk about here, and that is early on, okay, I said that this thing was a conductor. Okay. It's a piece of metal. Woo. And why does that matter? Okay. Well, if I put one positive charge on here, boop, and then I put another positive charge on here, boop, all right, you got to realize that that's electrons that can rearrange themselves to give the illusion that there's a positive charge. So it's really a hole, okay, it's really a hole where we're missing electrons. But those positive charges are going to feel each other, and they're going to get as far away from each other as possible. Okay, far away. So they're both going to end up on the surface somewhere. Okay, on the surface somewhere. All right. Now, let's suppose I keep pulling out electrons, so I keep making it more and more positively charged. Okay, and so if we do that, what we're going to end up is with a uniform charge distribution across the surface, because all those little positive holes are going to want to get away from each other. Okay, and if we try to put a positive hole in the middle, all right, it's going to get pushed around, and all the other little positive holes, they're going to rearrange too, and we'll have them back on the outside. So every time we put one on the outside, put a charge in this thing, boop, it goes to the outside. If it's a conductor, okay, because they move around and they want to get away from each other. So they spread out and they minimize their energy configuration that way. Now, what that means though is on the interior, okay, there's no electric field in there. Okay, it cancels out completely. There's no electric field. So inside any conducting material, there's not an electric field. Okay. Now it also tells us because it's a metal, and because all those positive holes or those charges go to the surface, we know we've got an equal potential surface on the outside. And that means it's going to be perpendicular to the electric fields. And that's how I knew to draw those field lines coming off straight off of the object. Okay, so if we have a metal object, the electric field lines are going to go perpendicular to the surface of that object. All right, they're just going to intersect that way. Okay, now, all right. Now, if it wasn't a conductor, if it was an insulating material, then we got to back some stuff up. Because if it's an insulating material, then if I put a charge on that thing somewhere, the electrons don't like to move around very well in insulators. And so whatever charge I put there is probably going to stay there. Okay. So it's kind of weird, if you are standing there and you got a balloon. All right. And let's say you have hair, unlike me. Okay. And you got your balloon here. Okay, and you rub the balloon in your hair, what ends up happening is you end up getting a lot of charge on one side of the balloon, but not the other. Okay, because the rubber doesn't like to move the electrons around. Okay, so if you either take some out or add some to it, they stay put. They stay put. Okay. And I suppose if you wanted to work really hard, you could get one side of the balloon charged positive and the other's charged negative, but that would require lots of planning. But you could theoretically do that. You could. Okay. So in almost all these problems, we're going to see that it's a conductor, because that makes it easier to deal with the electric field. If it's a conductor, we know the electric field's coming straight off of it. Okay. With our balloon here, if those are positive charges, okay, then I'm going to get an electric field that comes out this way because it's a point charge. But over here off the surface of my balloon, okay, it's going to be like this because it's kind of like coming from here. Okay. All right. So I'm not guaranteed that the electric field will be perpendicular to the surface. All right. And that also means if I look at if I measure the voltage around on the balloon, it's not uniform either. Okay. All right. There we go. Get it all on there. Okay. So that should equip you to be able to get going on your homework. All right. Give you all the information that you need there. And all right, I'll let you go.